Chapter 15.7, the second law of thermodynamics. So we've already seen the first law of thermodynamics, delta U equals Q minus W, and that really just deals with energy conservation. It focuses on both heat and work, and how we have to consider both of them to see how the overall energy changes in the system. The second law is a statement about the natural tendency of heat to go from hot to cold. So here's the second law of thermodynamics in terms of heat flow. We'll also later see it in terms of entropy. But in terms of heat flow, the second law of thermodynamics says heat flows spontaneously from a substance at a higher temperature to a substance at a lower temperature and does not flow spontaneously in the reverse direction, right? If you have a cup of coffee, that's a hot cup of coffee, you're going to find that your hands gradually get warm and the coffee gradually gets cold, right? The heat flows from the coffee to your hands in the environment. But if you have a cold cup of coffee, it's not going to suddenly spontaneously get hot again. That's just not how things work, right? So both the first and the second law of thermodynamics are really useful in describing things like a car engine. And a car engine, it turns out, is a great example of something more generally known as a heat engine. So let's take a look at what a heat engine is. So section 15.8, heat engines. Heat engine is a really general term to describe a broad category of engines. It's any device that uses heat to perform work. So it has three essential features. One, heat is supplied to the engine at relatively high temperature, from a place called the hot reservoir. That's what's shown up here. We have a hot reservoir, and that gives heat to the engine. Part of that input heat is used to perform work by the working substance of the engine. So the engine is able to do work, and doing work is good. That's how we get motion, so our car can start running, right? But not all of the heat goes into work. The remainder of the input heat is rejected to a place called the cold reservoir. This is sort of the waste heat, the exhausted heat. So a few key terms here. QH is the magnitude of the input heat, the heat from the hot reservoir. QC is the magnitude of the rejected heat, the heat that goes to the cold reservoir. And then W is the magnitude of the work done. So we will work with these magnitudes and we'll keep in mind the direction that they're going, that we have QH going in and work and QC going out. All right, now our goal here is we want to get work out of the engine, right? We want our engine to work. And what we're putting in to make this happen is QH. So our efficiency of how good the engine is going to be what we get out of the engine relative to what we put in. So the way we can calculate that, so on the next slide here, efficiency of the heat engine is defined as the ratio of the work done, what we want to get out of it, relative to the input heat, what we put in. So this is a great equation here. Efficiency is the little e, and you can divide the magnitude of the work done by the input heat. And that tells you how efficient it is, how good your heat engine is at converting the input heat into work. And we'll see it's never 100% efficient. There's always going to be lost heat. But if there are no other losses besides these three forms of energy, of heat and work, then we find that the energy we put into the engine is equal to the energy or heat coming out of it, right? So the energy and heat going in is QH. That's the heat gained by the engine. That's the same as the heat lost by the engine, which is the work plus QC. So that's another energy conservation right there, right? What goes in is what comes out if we don't lose it some other part of the environment. And we can use our definition of efficiency to actually get another relationship here, the one that's shown below. So I'm going to first solve for work by subtracting QC the other side. And I'm not going to draw all the magnitudes just to save a little bit of drawing time, but you can know that they're implied here. So work is equal to QH minus QC, subtracting that over there. QH minus QC. Great. This is just a rearrangement of the equation. Now we're going to divide both sides by QH. So do that to the left, do that to the right. And if you notice on the left, now we have work divided by QH. We just saw that up here. That's our efficiency. So this we can now write as efficiency E. And then this is equal to, if we split this into two separate fractions, right? I could write this as QH divided by QH minus QC over QH. With, again, the magnitude signs implied here. Now note, QH over QH, that's just equal to 1. And so that's how we can get to this equation shown, that the efficiency is equal to 1 minus QC over QH, which is a handy relationship when working with heat engines. All right, now that we're armed with this better understanding, at least of the very basics of how heat engines work, some of the equations that describe it, let's try out an example. All right, so example 6, an automobile engine, right? That's something we've all experienced in some form. I haven't personally worked on many automobile engines. It's a bit of a mystery, but the physics is something that I can understand. So it says an automobile engine has an efficiency of 22% and produces 2,510 joules of work. How much heat is rejected by the engine? All right, so our first step is we want to identify the variables given to us, and we want to specifically connect them to those 4 variables we just got defined for heat engines, right? So this efficiency of 22%, that's going to be our E. So we know that that is 22%, but if we want to write it in decimal form, I would then write that as 0.22. Right, so there's our efficiency, and then we know we have work. Cool, work is 2510 joules. All right, and what are we solving for? We're solving for how much heat is rejected by the engine. So this is going to be QH or QC. Remember, the rejected heat is QC. All right, and that looks like about it that they give us. So let's think about what equations we have. Well, one, we can look at our conservation of energy equation, that the amount of heat coming in, QH, is equal to the work done plus QC. So this is good. It has QC and work, which are 2 things that we know. So that's nice, but we don't actually know anything about QH here. The problem doesn't tell us anything about the input heat. So that's a bit less nice. But is there a way we could figure out QH? Well, remember the other equation we got for efficiency, right? We saw that efficiency is equal to the work divided by QH. We don't know QH, but we do know work and efficiency. So that would allow us to solve for the QH here, right? We can see that QH is just going to be the work divided by E. And so if we want to solve for QC, it'll be QH minus W. And we now know what QH is. We could plug in numbers if we want to, but we also don't have to. So QC is equal to QH minus W. And QH I could just write as work over the efficiency minus the work. And that will then give me QC. And it will have what units? It's going to be joules, right? Because heat is energy. So let's check our calculation setup here. Right, so we again have energy in is equal to energy out. That's great, and they solved for QC. QC is equal to QH minus W, great, and QH, yes, from the efficiency is equal to work over efficiency. So sure enough, we get that same expression. So the work we did matches up, awesome, right? We can factor out the work even, if you wanna save yourself a little work, and then you just have work times the quantity of 1 over E minus 1. Just have to be really careful with your algebra there. So if you plug in the numbers, you get 8.90 times 10 to the third joules. It is joules still, right? So that's 8,900 joules of energy. That's pretty good. So this is our general introduction to heat engines, and we'll get into a specific form of the heat engine in the next section, what's known as really the ideal heat engine. So stick around.